Back in Chapter 3, Section 1, we learned how to solve homogeneous differential equations with constant coefficients. That's the same title of this section, but in this section we're going to be dealing with higher order differential equations. Also in Chapter 3, we learned something called the method of undetermined coefficients. That was Section 3.5. And then in Section 3.6, we learned about variation of parameters. In Chapter 4, now that we've dealt with the theory, we're going to be learning about homogeneous differential equations with constant coefficients, the method of undetermined coefficients, and the method of variation of parameters as they relate to higher order differential equations. This section is about homogeneous differential equations with constant coefficients. I want to start by trying to draw a parallel between what we learned in Section 3.1 and what we're going to be learning here. In Section 3.1, we started by recognizing that second order differential equations that took this form, second derivative of y with respect to x, or let's do it with respect to t, second derivative of y with respect to t, is an equation of the form a function f containing a t, a y, and a first derivative. Now, this is just the form of the function. An example might be y double prime equals 3x, oh, I keep using x, 3yt plus 2y squared minus 5t squared plus y prime. That's a second order differential equation of the form f is a function of t, y, and y prime. Now, usually we put these in a different order. We'll say, for example, that this function f is, let's say, a function of t, so there are no y's in that term, minus a function of t times the derivative of y, minus a function of t times y, and that's our function f, f of t, y, and y prime. And I've been saying that that's equal to y double prime. If I now reorder this so that I have y double prime plus p of t times y prime plus q of t times y equals g of t, I have this second order differential equation in something like a standard form. If I'm not going to restrict myself to second power differential equations or second order equations, I might have, for example, the nth derivative of y plus, let's go with our subscripts here, p sub 1 of t times the n, got my thing in the wrong place here, the n minus 1th derivative of y plus p sub 2 of t times the n minus 2th derivative of y, and so on, right? All the way down to p sub, I'll come back to that, p sub something of t times maybe the second derivative of y plus p sub something else of t times the first derivative of y, the 0th derivative of y. And then because we're dealing with homogeneous equations, we'll just say that that's equal to 0. Now, that could be g of t, that could be a function of t, but in this case, it's just 0, and 0 is a function of t, right? Here's a polynomial in t. f of t equals 0 t squared minus 6t plus 0. Well, that's just equal to 0, right? So here I have a function of t that is 0, the constant function 0. So g of t equals 0. 0 is a function of t. It's perfectly legitimate to say that. But because it's 0, we call this a homogeneous differential equation. Okay, so that's what's going on there. Now, we've already discussed the fact that 0 is a function of t, and so I could put a 0 in here. Oh, I never put my subscripts in, did I? Let's see, I'm going up. So if I have n terms, then I'm going to have p sub n here and p sub n minus 1. This would be p sub n minus 2. Now, we don't typically write all of these. You might write the first two terms and then the last one or two terms. The implication by these dots here is that all the stuff in the middle doesn't vary. It doesn't vary in its pattern, at least, right? We know that if we're going down from the nth derivative to the n minus first derivative, and you see this dot, 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 this ellipsis here, then the assumption is that the next one down would be the n minus 2th derivative, and all the way down to the 0th derivative. Equally, if you're starting with p sub 1 here, the next one's going to be p sub 2, p sub 3, and so on, and then all the way down. Now, notice that we're taking n derivatives, or we have n derivatives, and we have p sub n as our last term here, but there are actually n plus 1 terms here, because I'm starting with the p sub 0 here, which I haven't actually written, p sub 0, and it goes up to p sub n. I'm starting counting at 0. I end with the 0th derivative, and I go up to the nth derivative. So I actually have n plus 1 terms in this equation. The next observation that I'll make is that these p sub 1's, right, because 0 is a function of t, any of these functions of t can be written as 0 or any other constant. So, for example, I could also write this as the nth derivative of y plus, let's just call it a sub 1, the n minus first derivative of y plus, and I'll go down to my a sub n times the 0th derivative of y. That is the same equation as that one, except that instead of implicit functions of t, I just have constant coefficients. Remember also that whether there's a function or a constant in front of y here, I can divide the entire equation through by that function or by that constant, so that there isn't one, so that the coefficient of the highest order term, that coefficient is 1. And that's essentially what I've done here. Just I've done it implicitly. I didn't talk about doing it. I just started with the equation in that form. If we now recall from chapter 3 that solutions to, let me go back to a second order equation again, specifically example 1 in our textbook in section 3.1 asked us to solve this equation, and we did it by noticing that if we take a function, that's going to be our solution, right? Y equals some function. If we take a function and we take its second derivative, when you subtract the original function from its second derivative, you get 0. What that means is that these two functions have to be the same. I could add y to both sides here, and I'd get this equation. Whose function is the same as its second derivative? Well, that's e to the t, right? So we say that one solution to this equation is y equals e, what's happened here, e to the t. Another solution turns out to be e to the negative t. Another solution turns out to be e to the c times e to the t. Let's call that one c1. How about this one's c2? And in general, I'm going to call this one y1, y2, y3, y4. In general, we discovered that the solution could take the form c sub 1 e to the t plus c sub 2 e to the negative t. And the reason for that is that if c1 is 0 and c2 is 1, you get this solution. If c2 is 0 and c1 is 1, you get this solution. If c1 is 0 and c2 is anything other than 1, you get this solution, and so on, right? So because c1 and c2 could be any real numbers, the possibility that c1 and c2 are either 1 or 0 in combination means that all 4 of these solutions are possible just from writing it out this way. So we call this our general solution. In fact, as it turns out, we can put a constant in front of t as well. Those c1 e to the rt plus c2 e to the, let me try to fix that. I'll just do it this way. Just rewrite that whole exponent. Negative, where'd my pen go? Negative rt, right? This is my general solution. So the key here, what I want you to take away from this review is that equations, or solutions rather, look like this. Now what I'm going to do is erase some of the top part of the screen here. So if you need to pause the video for a moment and write any of that down before I do that, please go ahead and do that now. I'll erase some of the top part of the screen, and we'll use what we've discovered or rediscovered down here to address the case where we're looking not just at the second order differential equations, but nth order differential equations. So let's do some erasing. And then let's move this up here. And I think I'll leave that where it is for the moment. And then let's take our solution y equals e to the rt, and let's take a few derivatives so we know what kind of pattern to expect. Y prime is going to be r e to the rt. Y double prime is going to be r squared e to the rt. Y triple prime is going to be r cubed e to the rt, and so on, right? So it appears that our nth derivative is going to be r to the power of n e to the rt. So now I can write this as y to the nth derivative of y, which is r to the nth power e to the rt, plus some constant times the n minus 1th derivative. Well, the derivative I take seems to match the exponent, right? So my derivative here is going to be, n minus 1th derivative is going to be r to the n minus 1 times e to the rt, plus the next term would be a sub 2 times r to the n minus 2 times e to the rt, all the way down to a sub n times the original function, which is e to the rt. I could write that as r to the 0 times e to the rt, and that would give me, where's my pointer, r to the n minus 1, r to the n minus 2, r to the n minus 3. Those are all in here. R to the 3, r to the 2, r to the 1, and then r to the 0. That would go in here, r to the 0. Well, that's just 1. So that's why that appears to be missing in this term. Now, recognizing that what I'm doing is rewriting this equation, this generic equation, in this form, replacing the nth derivative of y with what I now know its nth, what its derivative is, right? I need to include at the end of this equals 0. Okay, so now that I have written this equation as this equation, all I've done is replace each generic derivative of y with its actual derivative, which is this piece right here. The a sub 1 is just a coefficient, remember. I can factor out that e to the rt, so let's do that. E to the rt times, in the first case we have just r sub n, then we have a1 r to the n minus 1, and we're going to have, I don't have that term here, I haven't written it out explicitly, but the next term would be a sub 2 r to the n minus 2, and so on, down to the a to the n minus 1 times r to the 1, and a to the n r to the 0. And that still equals 0. Let's see how much moving around I have to do here to squeeze that in. Equals 0. Now your textbook has a leading coefficient here of a sub 0. I'm going to squeeze that in just to make sure that I'm consistent with your textbook. But again, I'll just remind you that I can take p naught, whatever p sub 0 is here, and divide the whole thing through by p sub 0, leaving me with, just from previous examples, if I have p of t times the nth derivative plus, let's go with p sub 0 and p sub 1 of t times y to the n minus 1st derivative plus and so on down to p sub n of t times y, the 0th derivative of y, move that over here, equals, in this case, 0. Let's go ahead and call it g of t, because that could be 0, it could be anything. So this is a good review of the general case. Then if I want to, I can just divide both sides by p sub 0. And that gives me p sub 0 divided by p sub 0 is 1. So I get just the nth derivative of y. Plus, now I'm going to have p sub 1 divided by p sub 0. And I'm just going to call that my new little p, small p, sub 1. And then my next one would be, my next term would be p sub 2. It's in here somewhere. P sub 2 divided by p sub 0. I'm going to call that little p sub 2. My pen just stopped working. There we go. Little p sub 2. And I forgot my y in here actually too. Let me back up a little bit. This is my y sub, or y, n minus 1th derivative of y. And then I'll have p sub 2 of t times the n minus 2th derivative of y, plus and so on, until I get to p sub n divided by p sub 0. I'm just going to call that little p sub n. I hope that you can see that these are supposed to be capital P's and these are supposed to be lowercase p's. That's the only difference. So all I've done, and I'm not even going to finish this because I hope you are, this is review. We've done this a number of times now. I've been working with this equation, right, which started with just r to the nth power. Your book has an a sub 0 in front of it. My claim is that if a sub 0 is not 1, I can divide through by a sub 0 so that a sub 0 could be 1. You know, if this was capital A sub 0 and that was not 1, then I could divide everything through by capital A sub 0, and that would give me small a sub 0 equals 1. So I've added those in there just to be a little more consistent with your textbook, but they're not strictly speaking necessary. Okay. Now that's a little messy, so what we're going to do now is just give this, let me grab a highlighter real quick, give this thing here, which is just a polynomial, right? We factored the exponential out of it. Color that in real quick. We're going to take this thing. The a's are just coefficients, or constant coefficients, and the r's, r is essentially a variable, right? So this is just a polynomial. So we're going to call this thing z of r. It's a function. The z of r is just a function whose variable is r. Like f of x is just a function whose variable is x, right? So that's all that is. And then I'm going to say that that's equal to 0. So now it's a lot easier to see that by the zero product property, that either, that double arrow means implies, this statement implies or means that this statement must also be true. And so what I'm implying here is that either e to the rt must equal 0, or the function z of r must equal 0. Well, e to the rt can't equal 0, because if I let r equal 0, or even t equal 0, I get e to the 0, which is 1, not 0. So this can't be true. This assumption, right, that if this product is equal to 0, that either this factor or this factor must be equal 0, that implication holds, but as it happens, the first one doesn't hold, can't hold. This cannot be true. So it must be then that, get my highlighter again, that z of r equals 0. So I can use this to find the values of r that make the original equation, if you will, that make that true. Now, before we go on, I want to highlight something here, literally. I don't want us to forget that we've decided that y equals, I don't like that color. Let me back up and do something different here. Y equals e to the RT. That's not very good either. Let's just try white. Y equals e to the RT. That is a solution. Because of the type of equation this is, that is a solution to our differential equation. So y equals e to the RT is a solution. E to the RT equals 0 does not contribute any additional solutions. So there's a distinction to be made there, and I think it's very important. So we have, I'll tell you what, let me try highlighting one more time, and this time I'm going to use yellow, if I can get my pen to work. All right, so I've got y equals e to the RT, and I've got z of r equals 0. Those are my solutions, or those are the sources of my solutions. And we've actually been here before. We didn't have anything like this complex. We didn't have this many terms, but we had this thing, I'm just going to go ahead and call it z of r. We called it the characteristic equation, and that's exactly what this is here, characteristic. I can't talk and write at the same time. All right, and the highest power of n we've worked with in the past is 2. So our characteristic equation was just a quadratic. Solve the quadratic. This quadratic equation equals 0. And you have values of r. So the solution of this will produce values of r. And those values of r give you the solutions. The solution number 1 would be e to the first value of r that you find, and so on. We did this before. We had 2 different values of r because r was just the characteristic equation was just a quadratic. So that gave us 2 solutions. In this case, we're going to have n solutions. And I hasten to add that those are n solutions to the characteristic equation, not n solutions to the differential equation. N solutions to this characteristic equation give me the values of r for which this statement is true, and r goes here. Let's go back now and look at the section titles in Chapter 3. Section 1 was Homogeneous Differential Equations with Constant Coefficients. And that title matches exactly the section that we're working on now, Homogeneous Differential Equations with Constant Coefficients. In this chapter, Chapter 4, we're working at a higher degree. So that's the difference there. The next section in Chapter 3 was called Solutions of Linear Homogeneous Equations, the Wronskian. And the Wronskian was the thing that helped us determine what the solutions, the first time we did this, the solutions to the characteristic equation were. And because it was the first time we were doing it, we stuck to solutions to the characteristic equation that were real numbers and that were distinct from each other. So if you remember factoring a quadratic, let's say that it ends up, I'll write this down, let's say that it ends up being factored so that it looks like x minus 2 x plus 3, for example, equals 0. Then the 2 solutions we're going to get from this are x equals 2 and x equals negative 3. And those two values are different from each other. They're real numbers and they're different from each other. Compare that to the case where you end up factoring the quadratic and you end up with something that looks like this, x minus 2 equals 0. The solution here is x equals 2 with a multiplicity of 2, or you could write it just like this, right? Those are non-distinct real roots or real solutions to this quadratic. Now the quadratics that we were working with before were characteristic equations of differential equations. So we need to find the solutions to those quadratics, or in this case, my pen has stopped working again, the nth power polynomial, nth degree polynomial, find the solutions to that, find the solutions to this ZR. That's all we're doing here is calling this long polynomial a function of R. We're going to find the solutions to this thing by setting it equal to 0, right? And we're going to do that by, first of all, finding distinct real roots. So real number roots, real number solutions to the characteristic equation, and roots that are different from one another. Okay, so our first example, which I'll do in just a minute, deals with distinct real roots, which in your textbook, for some reason, they've decided to call real and unequal roots. So just above where is it? Just above example 1, there's a brown subtitle called Real and Unequal Roots. So that's what we're going to be doing first, and that matches up with the 3.2 solutions of linear homogeneous equations, the Wronskian. The next section in chapter 3 was called complex roots, and the one after that was called repeated roots. Both of those are covered in chapter 4, section 2. So I'll probably start a new video to cover these. We do non-repeated real roots, so distinct real roots first, and then complex roots, and then lastly, repeated roots. Those are all in 4.2. After that, we got in chapter 3, section 5, method of undetermined coefficients. And if you look down, section 4.3 is also the method of undetermined coefficients. And after that, variation of parameters, both in chapters 3 and 4. So as you can see, these two chapters really parallel each other. And chapter 4 is really just a look at what happens to the various strategies that we learned in chapter 3 at a higher degree of differentiation. So I'm going to stop this video here, and I'll pick up where I left off in chapter 4, section 2, and we'll start with that first subsection that your textbook calls real and unequal roots, distinct real roots.